Hello, everyone. My name is Haifeng Zhao. I'm a PhD student from the University of Sydney, and my research topic is about wearable, augmentative, and alternative communication devices for people with cerebral palsy. And today, I'm presenting you a survey. So please allow me to share the screen first. So today I'm presenting you a survey, augmentative and alternative communication with eye gaze technology and augmented reality, reflections from engineers, people with cerebral palsy, and caregivers. Before I start the presentation, I would like to thank to the support from the University of Sydney and the Cerebral Palsy Alliance. The ethics of this project has been approved by the Human Research Ethics Committee from the University of Sydney, and it is partly sponsored by the Neurodisability Assist Trust from the Cerebral Palsy Alliance. I would also like to express my thanks to the CP Register from the Cerebral Palsy Alliance, who helped us recruit our target group participants. Please let me introduce you some background of this study. Cerebral palsy is one of the most common physical disabilities. It affects a person's posture and control of the movement. It is a permanent lifelong condition, but generally does not worsen over time. It is due to damage to the developing brain either during pregnancy or shortly after birth. About half of people with cerebral palsy have a speech disorder, and 1 in 3 of people with cerebral palsy are nonverbal. The permanent treatment is still under investigation, and the current one of the most frequently used solution is the augmentative and alternative communication. It is a group of technology that empowers people to communicate with others without speech or writing. The current AAC equipment is all based on desktops, which usually mounted on users' wheelchairs. It is usually described as lacking privacy, portability, and engagement. Therefore, we proposed a novel solution using an augmented reality-based eye gaze technology. The fundamental components of the proposed design were HoloLens from Microsoft, and eye tracking plug-in system are from the Pupil Labs. HoloLens is a pair of glasses which provide an immersive AI environment, and the Pupil Labs designed a 3D printed frame to hold their eye tracking system on HoloLens. With the combination of these two technologies, we moved the communication board from the desktop to the AR glasses. With our prototype, users can use their eye movement to control a pointer if they hold their gaze on one word for about 1 second. The word will be selected and spoken out by the HoloLens speaker. Please allow me to show you a demo video of me using the devices to compose a sentence, "I am happy." Before I start the video, I will just share the sound of the video. Okay, let's try.
I am happy.
You may have noticed that in the video there were 3 dots rather than 1. The white one was an indicator for left eye gaze pointing, and then the blue one was for the right eye. The right pointer in the central was the indicator of 2 eyes middle point, which would be the selector of the communication board. The vocabulary was selected based on most frequently used English words from previous studies. The current design is just the first step to a more comprehensive multi-option and more stable variable AAC system. Therefore, we conducted this survey to understand how people would think about using the proposed design as an AAC method. We made a demonstration video with a detailed introduction of the system and the recording of the developer using the devices to calibrate and compose a few sentences by using eye gaze. The video I presented today was only part of the demonstration video. The whole demonstration video is about 4 minutes. This video was then embedded in a survey hosted on the Red Cap. The survey was then distributed through multiple channels, including leafed flyer, social media posts, email through CP Register. We aimed to recruit engineer students or academics, people with cerebral palsy, and their caregivers. The engineers could help us to evaluate our design from a professional perspective. The people with cerebral palsy and their caregivers could help us to understand the user's perceptions. The survey comprised the three parts: basic information about the participants, adjusted cubic user evaluation of satisfaction with assistive technology, also known as the Quest 2.0, and the adjusted NASA task load index, also known as the NASA-TLX. If the participants were engineers, they would be asked for which discipline they are in. If the participants were people with cerebral palsy or caregivers, they would be asked for their mobility and the communication level by using tools gross motor function classification system, the extended and revised version, manual ability classification system, communication function classification system, Viking speech scale, and current communication method. After this, the participants would be promoted to the demonstration video as well as a description image of the HoloLens size and weight. There was also a reference image of an iPad Pro on the side to illustrate how heavy the HoloLens is. So basically, the HoloLens is as heavy as an iPad Pro. And then the adjusted Quest 2.0 was present. The original questions of Quest 2.0 were about satisfaction levels of the device's dimension, weight in adjusting, safety, durability, easy in using, comfort, effectiveness, and privacy. As our survey was conducted online, the original questions were interpreted as perceived experience by watching the video. Similarly, the original NASA-TLX was also interpreted as perceived workloads, such as perceived mental demanding, perceived physical demanding, perceived temporal demanding, and developers' overall performance and perceived efforts to finish the task. After 3 months of data collection, we got responses from 25 participants. The participants were divided into 2 groups. Group A, engineering students and engineering academics. Group B, people with cerebral palsy and their caregivers. 19 of the participants were Group A participants, and other 6 were Group B participants. The overall average age was 31.24. The average age for Group A was 27.53, and the average for Group B was 33. The results showed that the Group A were more satisfied with the devices than Group B, except for the weight. For the most important 3 factors, both groups agree that ease of using and comfort are the most important 2 factors. The Group A expected the effectiveness was one of the most important factors, but Group B seemed to have different opinions for the third most important factor. Nevertheless, effectiveness was also considered as important in Group B. For the NASA-TLX, Group B seemed to be more tolerable to the workloads than Group A, especially for the mental demanding, and for the overall performance. Both groups give high marks. So in a nutshell, the proposed solution was perceived favorable by both engineer students and the academics, as well as people with cerebral palsy and their caregivers. The engineers were more satisfied with the devices. It may be because the people with cerebral palsy expected to use the final product in their daily life. Hence, they expected higher durability. However, regarding the weight, the people with cerebral palsy usually use wheelchairs, which give them height and neck support. It seemed that the weight was more acceptable to the people with cerebral palsy than engineers. Additionally, the people with cerebral palsy usually use the accessible equipment on a daily basis. They appear to be more familiar with such workloads. The conventional communications such as speech and writing are very intuitive and quick. This may make the engineers to expect the AAC would behave similarly. Apart from the feedbacks from the participants, they also found a major drawbacks of the system. As the HoloLens and Pupil Labs were not integrated system, the eye tracking was very sensitive to the movement. This version of the HoloLens did not have any holder or supporter on the top of the head. The gravity made the HoloLens shift its position constantly, which made the eye tracking less effective after a long time wearing. The second version of HoloLens, the HoloLens 2, however, has an embedded eye tracking system, which is more robust in regard to the movement. Moreover, the brain and computer interfaces technology enables people to use electroencephalograph, the EEG, to control the computer could help people to use the devices to communicate with minimum movement input. This would be a more inclusive solution for people with severe neurodevelopmental disorder. For the next step, we are looking forward to upgrading our design by using HoloLens 2 and BCI. This study is in progress and the current results seem to be very positive. In our next paper, we would also talk about this improved wearable AAC system. Thanks for your attention, and please feel free to ask any questions, and I would be very appreciated if you leave any comments. Thank you.